Okay, let's start with rotational form of Newton's second law on page 342. So we're going to consider a point mass located at the end of a massless rod which points at one end. That's the left end, okay? A top view is shown. That means the gravity is acting into the page. And we will draw a free-body diagram for the mass as viewed from above. And the plane that we see is XY plane. So in this case, think about which way the gravity pointing. Into the page, is it positive z or negative z? You gotta go in a cyclic order. Again, that's all about the cross product, and we are focusing on cross product in this chapter. So you have to go like x, y, z, and that means z is coming out of the page, and negative z is into the page. So gravity is pointing along negative z direction in this case. Okay, so that's not the focus. I just want you to think about it. But we're going to focus on this force F, and particularly since there's rotation, which component contributes to rotation, and we're going to focus more on that. Okay, but let's understand the free body diagram first. So this is a point mass and a massless rod. It's like kind of a rope attached to a mass, and you're rotating it, okay, because it's then because the rod doesn't have a mass. So what force is acting on the mass? So we can see F, and has two components as we discussed before. We have the radial force, radial component along this R direction, because R is our radius, right? And tangential one is perpendicular to this R. So those are the components of F. What else do we have? So we have this contact here, and then we have this force F, but there's another contact with the massless rod, right? And if you think about what we did before, like again, if you assume this massless rod being a rope, so that there's going to be a tension, there's going to be a pull force, right, on the point mass. So it's going to be, this point mass will be pulled towards the pivot point. So that's the reason that we call this force T. It's like tension, but some contact force. Okay, that's what you need. And another way of thinking the direction pointing to the left towards the center is because we will have radial acceleration. And if you look at the forces before tension, we have only radial force pointing away from the pivot point, but we need something pointing towards it, and that has to be greater even, because we need to have a net force towards the center of the rotation, right, to have this radial acceleration. Again, that's not the focus either, but I want you to analyze the problem carefully first. And so this kind of tells me that tension force should be greater than the radial force, so that there will be net force towards the center that will give you the radial acceleration. Okay, so first we will start with Newton's second law, and we are focusing on the y-axis because that's the force that creates the torque. Ability to rotate only is on the Ft. So sum of Fy becomes Ft, right? And MAY is simply the tangential acceleration. AY is AT, because again it's along the tangential velocity, right? This is the direction of AT. So we recall, for a rotating object there are both normal and tangential accelerations, and now we multiply both sides by the radial distance. So we're getting this equation multiplying by radial distance. On the left side we have RFT, on the right side we have RMAT. Okay, so again, R times Ft is going to give us the torque, right? Because remember, torque is R cross F in vector form. In magnitude form, RF sine theta, but in this case, Ft and R, so if you take this F to be Ft, you have 90 degrees, and this is simply 1, so it becomes RFT. So you can replace RFT with torque, as we do it here. And on the right side, you can introduce you can kind of convert AT to alpha, like angular acceleration. You can introduce angular acceleration using the definition as we discussed it in the review. Hopefully it's refreshed. So AT is R alpha, and then you're just putting R alpha here. There are two R's now, so you're going to multiply them and you're going to get mR squared alpha. Okay, that's the torque. So if you look at this equation carefully, what is mR squared? We just did a review, right? Can you see what it is? It is in the form of inertia, right? Moment of inertia. And alpha is the angular acceleration. So you can kind of generalize this equation as torque is equal to I alpha. Okay? And since we had a point mass, and this is true only for point masses, then you can convert it to inertia, moment of inertia of a point mass in this case, in this problem. But the point is to get from the Newton's second law, from the force and acceleration form to torque and angular acceleration form. Okay, and that's what we got. So this is our kind of the second law. If we want to be more specific, instead of having just one torque, maybe we'll have a bunch of them and we need to find a net torque. So what we will do then is to sum up all the torques and make it equal to moment of inertia times the angular acceleration. That is the general form. That is the Newton's second law in rotation form. Okay, so this is the third form, right? We did F is equal to ma, then we did F is equal to dp over dt, the momentum, change in momentum. And now this is the rotational form, torque is equal to I alpha. Okay, that's the third form of the second law. And so if you compare it with the linear form, the left-hand side is the sum of all torques acting on the object instead of the sum of all forces. And the moment of inertia replaces the mass when we switch to the rotational problems, as we talked about the mapping before. M goes to I in the rotational form. And we use the angular acceleration instead of translational acceleration. So what we are doing is we really added one more mapping. Okay, let's check that here. So we already have M goes to I. Now we also said force in the rotational form is torque. Okay, so you had F is equal to ma. Just using the mapping, I can now write the rotational form of second law. Torque is equal to I alpha. Okay, and once again, this force and accelerations are vectors, and torque and angular accelerations are also vectors. Most of the time we don't put the vector signs on the torque equation because we're just kind of going to do like we are doing simple stuff, and alpha is going to have only one direction, and so you don't have to worry about splitting into components as we did with the force. So it's, if you ask me, it's easier because it's just not less complicated in terms of math, but at the same time, because of that cross product up here, as we discussed earlier, that makes things a little bit more complicated. Okay, so after this we are going to practice and we're going to solve the next example.